parameters. Okay, whatever wing parameters we have. Okay, so by using that 2D wing parameters, we'll be creating our 3D wing in the OpenVSP software. So here I will just recap about the wing, what I have discussed in my 10th class. Okay, so class 10. Okay, in this class 10, I'll just recap just by running the slides, whatever I have discussed in the class 10. That is introduction to wing construction. Okay, so I have told about the basic about the wing. Okay, the flying bird wing section. Okay, and we have different wing cross section. Okay, for different but similarly we have different wings for our aircraft. So based on bird's wing, and that bird's wing what we have based on that picture, or based on that flying principle, we have designed the aircraft wing, or we have the aircraft wing. Okay, so this is what I have discussed in class 10, and also I have discussed about the wing design parameters. There are 18 design parameters. These are those. Okay, and wing parameters. What parameters here we have the same picture. Okay, root chord, tip chord, leading edge, steering gauge. Okay, and all other parameters in aerodynamic chord. So we can find parameter, that is aspect ratio, wing loading, chord, and here we have three wing with different taper ratio, and here we have wing with two sweep angle. First sweep angle is here and second sweep angle is here, and in our OpenVSP just we will split the section to get this kind of wing, or to create this kind of wing. Okay, and here we have five wing with different sweep angle. Here sweep angle is 0, and here we have some sweep angle, that is leading edge sweep angle with, and different rectangular wing. Okay, rectangular wing with the same planform area but different aspect ratio, AR. So this is what discussed in the classroom. So I hope got, or you have recapped your class 10 fundamentals. So why I have shown this fundamental, because based on this fundamental itself we will be designing our wing. So I'll jump to today's slide what we have. Yeah, so this is our today's slide. Design parameters. During the wing design process, 18 parameters must be determined. They are as follows: wing reference or planform area, commonly we'll call that as SW, or S reference area, or just S. Number of wings, vertical position relative to the fuselage, where you want to position your wing. Okay, above the fuselage or below the fuselage or mid-side the fuselage. Okay, there is high wing, mid wing, or low wing based on the position of your wing with respect to the fuselage. Here we have different names like high wing, mid wing, and low wing. Okay, and horizontal position related to the fuselage. Okay, how you will be positioning your wing horizontally or vertically. If you place horizontally, then we will call that as horizontal stabilizer. Vertically, if you place, then vertical stabilizer. Okay, and similarly cross section or aerofoil, aspect ratio, taper ratio, tip chord, root chord. Okay, mean aerodynamic chord, span, twist angle, sweep angle, dihedral angle, incident setting angle, high lift devices such as flaps, slats, okay, ailerons, and other wing accessories. So among all these 18 parameters, we may use some parameters now just to design one 3D wing by using that 2D parameter. Okay, we'll be designing 3D wing in our OpenVSP. You may get only 8 parameter, or according to your design requirement you may uh, calculate all 18 parameters or some parameters just for your required wing model, right? So based on the parameters, you'll be designing the wing, and this is what wing layout, root chord, CR, tip chord, okay, datum, leading edge, trailing edge, sweep angle, it, and overall B is a span length. This is all we already told. Okay, now this is our today's first question. That is, design a wing or design a 3D wing by using 2D wing parameter. So here we have the 2D wing. Okay, so by using this 2D wing and the design parameter like the span, that is 30. Okay, suppose that is meter or centimeter. Okay, or feet. At the end you can export as per your required unit, okay, or required measurement. So here what we have, the number that is non-dimensional number, so I'll call now this as a 30-meter wingspan, okay, chord 5 meter, no, just I'll, I'll just take a non-dimensional number, it's a 30, okay, chord 5, area 150, okay, and aspect ratio 6. And next what we have, the other parameter, root chord should be flat, tip chord should be flat, okay, incidence angle has to maintain 0, root incidence angle and incidence location, that is 0.20, leading edge clustering, okay, tessellation, just maintain this, and trailing edge clustering, maintain same value, and minimum leading edge to the trailing edge panel width this much, maximum growth ratio this much, okay, 1.180. And other parameter we have, that is section, first section and zeroth section, okay, sorry, yeah, here we have only one section, okay, and the aerofoil section 1 is giving idea about, see here, this wing has not been splitted, right? This wing here, by using or by seeing to this wing, easily we can say that this wing is not splitted, it's just only one section, so that's why section is only one wing section, okay, here there is no any split, okay, so that's why I can say the wing section is only one section, okay. And with respect to that wing section, we have the parameter span 15, area 75, taper ratio 0.66670, and sweep angle 0, sweep location 0. Sweep angle is 0, that's why see this side is 0, okay. And section sweep location twist, okay, twist location 0.20, okay. And aerofoil, which aerofoil has used NACA 2412, so NACA 2412 aerofoil has been used for this wing, okay. And other parameter related to the NACA series, that is thickness to chord ratio is 12%, camber is 2%, and location of camber is 40% from the leading edge. So here we have all these parameters, okay, the 2D parameters or general wing design parameters, okay. So now we will import all these parameters and we will generate or we will design a 3D wing, okay. So let's go to OpenVSP. So just double click on the software. As soon as we double click, we'll get two window. One is OpenVSP window and one more geometrical browser window. So by using this geometrical browser window, just select the wing and add. As soon as you select the wing and you'll add, you'll get default wing. Okay. So for this default wing, we have to use our required design parameters. These parameters, see, now in this uh, wing, okay, in this default wing parameter, what we have, the plan form, okay, parameter or total plan form parameter, span, projected span, chord and area. Okay, it's completely different, okay, as compared to our required parameter. Okay. Okay, see, in our case the span is 30, projected span 30, chord 5, okay, and area 50 meter square. Okay, span, that is length, I can call that as meter. Okay, now what we have to do, we have to change all this. Okay, span, as per our requirement, how much we have, span 30 meter. Okay, I'll use one standard unit, that is 30 meter. I'll call this non-dimensional number as 30 meter. And enter. 30 meter, 30 feet or 30 centimeter. Okay, so and then you can export. Okay, while exporting it will ask you, okay, in which unit you want, like that. So I'll tell that one. Yeah, let me now use these parameters. Span 30, projected span also 30. I will enter 30, here also 30. Next, chord 5, I'll enter. And next we have the area, that is 50 meter square. There is no any unit, okay, just non-dimensional number 50. I'll just type 50 and I'll enter. Now what is aspect ratio? 6. So as we know, area is directly proportional to aspect ratio. So wingspan and all. Okay, wingspan, aspect ratio AR is equal to B square by S. Okay, area and the span, these two are the parameters for aspect ratio. As we know, aspect ratio AR is equal to B square by S. B square in the sense wingspan and S in the sense wing area or area. So that's why automatically we get aspect ratio 6 for that case. Which we have here, area is 150, sorry, 150. Done, no? Yeah. Yes. And rest other things, I hope it's same. Yes. Cap tessellation 3. Okay. Root cap flat, tip chord flat. Okay. Incidence 0. Incident location 0.25. It's same. Okay. So I'll not do any changes because it's completely same. Okay, so now I will jump to next tab, that is the section tab. Okay, so here we have the section related parameters. Okay, here we have the section related parameters. I'll just enlarge this. So here the section wing section is only one section. Okay, so yes, it is only one section, and number of U6. Okay, root cluster 1, tip cluster also 1, span 15, area 75, 20 area 75. mm, Taper 0.06. Okay, projected span 15. Okay, sweep how much? Now currently here is 0, so we will go as per our requirement. Sweep will maintain 0, sweep angle. So I'll just change this sweep angle 30 to 0 as per our requirement. Okay, yeah. And next, mm, 001. Yeah, everything is same. So now I'll come to aerofoil section. Okay, aerofoil section. Which aerofoil section we have? Naka. Okay, the cross section type, that is 4 series, and the name of the aerofoil Naka 2412. Okay, let's check for default what aerofoil we have. Okay, 4 series itself, but the name of the aerofoil is different, 0010. So we have to change our Naka 4 series aerofoil name. Okay, 0010 into 2412. Okay, Naka 2412. This aerofoil we have to use for our wing cross section. Okay, the cross section type you have to choose this one, Naka 2412. So 2412 in the sense thickness to chord ratio is 12%, camber 2%, and the location of camber is 40% from the leading edge. So we have to import all these parameters. Okay, aerofoil parameters, thickness to chord ratio 0.12. Okay, percent camber 2%, 0.02, enter. And camber location, how much we have camber location? Mm, 40% from the leading edge. So here we have 20%, so I'll change 20% into 40%. So yeah, we got our required aerofoil Naka 2412. Right, Naka 2412. Right, and after this is not required. Let me do this. That is for next case. Yeah. Okay. Mm, everything is done now. So now I will shade. Okay, as per our given parameter. Okay, wing design parameters what we have. Okay, we have used all these parameters. So based on the parameters, okay, for this case one. Okay, based on all these parameters what we have. Okay, We have used all these parameters. Okay, and our default wing has been changed to our required wing. Okay, which means we have generated or we have designed our required wing. Okay, by using given wing parameter. So I'll just share this. I will use all four views. Yeah. Yes. So we have done with case one. Okay. So you can save your model. So initially this wing was not like this. Okay. It was like this, the default one. So for this default wing, we have changed default into like this as per our requirement, right? So this is how you can design a 3D wing by using 2D wing parameters. Okay, and next we have design of 3D wing by using 2D wing parameter. Okay, here we have not splitted, but in the second case, okay, the wing has been splitted, the first section and the second section. So now we will do this one. So we have to design a 3D wing by using 2D wing parameters. Parameters here we have, okay, span, projected span, chord, area, and also section 1. Okay, wing section 1. As I told you, here we have two sections. This one is our first section, and this one is our second section. First section and the second section. So for each and every section, what we have the parameters. Okay, for this complete one section and for this second section. So with respect to that, we have the section parameters, wing section 1 parameter and wing section 2 parameter. Okay, and also we have the aerofoil. Here we have the cross section type aerofoil, that is 4 series aerofoil, and the name of the aerofoil is NACA 2212. 2212 in the sense thickness to chord ratio is 12%, camber 2%, and maximum location of camber is 20% from the leading edge. So now what we'll do, we'll just delete all these things. Okay, and I will add the wing. See, in this case, only one part we have, which means there is no any symmetry. One more symmetry part. Okay, it's a half wing. Okay, you may call this one as a right side wing or left side wing. Okay, so now similarly, I will do here. I'll just off the symmetric part. Okay, with respect to the plane xy, with respect to the plane x and z, what we have the symmetry. of this wing, that I will off. Okay, and I'll keep only other symmetry. Okay, and I'll call this one as the right wing, and this one is left wing. So I don't want the symmetry one, I'll off. And here what I have to do, I have to come to the section first, and I have to split. Currently the wing is completely one section, complete one section, this. Okay, so as per our requirement, what we have to do, we have to split to this default wing as per our design requirement. Okay, you have to split into two sections. So I will split this wing. Currently the wing section is only one, you can observe. So what I'll just use this option, that is split option. As soon as I click on this, just observe, yes, wing has been splitted. This one what we have, the first wing section, and rest we have the second wing section. Okay, and this one is complete one wing section. For this complete wing one wing section, we have split it into two wing section. First wing section, I will call this part as a first wing section, and this part as a second wing section. Okay, so now I will use the design parameter. Okay, I will just come to plan or total plan form parameter. Okay, and I'll just input all these parameters, that is span 11, enter. Okay, wait, let me mm, cut the section. I'll cut once again, I'll add. Okay, let me delete all this. I'll add once again. I'll off the symmetry part. Okay, so first I'll just import all this parameter. Span 11 for this complete wing. Okay, for this complete section, span is 11. After using this parameter, then I will split. Okay, projected span 10.95, 10.95, 10.95 approximately equal to 11. So I'll just round off this to 11. Okay. Chord 3.25, and area 29.5, 29.5, enter. Okay, and next we have mm, cap distillation 3, incidents 4, incident location 0.25. I hope these all things are kept default, same value. Let's check. Yeah. Okay, rest of the things what we have. Okay, tip treatment and root incidents and distillation control, these are all default values. Okay, now I'll jump to next parameter. Okay, so that is section 1 and section 2. So now I will split this wing. I'll come to the section and I'll split this complete one wing into two parts. Okay, and I will call this as a part 1 and part 2, or section 2, section 1, section 2. Okay, so now I'll come to section 1 because I have to input the section 1, wing section 1 parameters. Okay, number of U22. I'll just type 22 and I'll enter, and root cluster 1, tip cluster 1. Okay, yeah, it's 1 1. Okay, let it be. And next span 3. Mm, okay, I'll change 4 to 3 as per requirement. And next we have root cluster, tip cluster 6 and 3 respectively. 6, enter, 3, enter. Okay, so you can observe as soon as I give the input, then changes has been done, right? Projected span 2.98. Let it be that default, because yeah, 2.98 or 3 approximate value. Okay, 2.9, I will just round off that to 3. Okay, 2.98 is nothing but 3 only. Okay, sweep, sweep 0, sweep location 2.0.25, and section sweep location 1. Okay, 0, 0.25 and 1. So I'll change this sweep 30° into 0. I'll enter, sweep location 0.25, enter, and section sweep location 1. Okay, it's 1 only. Rest other value, I hope it's same. Yeah, dihedral angle is given, that is 5°. Okay, dihedral angle is 5°. So I'll just input that value. Dihedral is 0, so I'll just change this 0 to 5 and I will enter. So whatever I have done here, that is affected only to the section 1, wing section 1. Okay, wing section 2 is as it is, because currently I am on with section 1, you can observe. Okay, currently I am on section 1, so that's why whatever input value I have given and whatever input value after giving whatever I have used the option enter. So after entering, the effect has been um, done to only wing section. Okay, okay, or the input value has been affected only to this wing section 1. Okay, now we will come to section 2 because section 1 is done. Okay, so now we will come to section 2. Okay, section 2, I'll jump to section 2. Section 1 is done now, just use this option, okay, or arrow, and come to section 2. So you can able to see the number also has been changed 1 into 2. Okay, so 1 and 2, right? Section 2, now currently you are on section 2. Okay, and we have to use all these parameters now. Section 2 parameter, number of U22, root cluster, tip cluster 1 1. Okay, I'll change 6 to 22, enter. Rest of the things 1 1. Section plan form, I'll check section plan form how much. Span 8, root cluster 3, and tip cluster 1. and is 8, enter. Cluster 3 and click cluster 1, enter. Okay. Yes, 7.96 approximate value, and that one we can round off to 8. So that's why uh, we can observe projected span what 8. Now next what we have the parameter sweep is 0, sweep location 0.25, and section sweep location 1. Okay, 0, 0.25 and 1. So here we have sweep 30. We don't want 30 because as per our requirement that is 0. Sweep angle is 0 for section 2. So that's why I will change this 30-degree sweep into 0 degree as per the design requirement. Okay. Sweep location 0 and section sweep location uh, sorry, sweep location we have the value 0.25. That is our wing parameter 0.25, enter. Section sweep location is 1. Okay, that's 1 itself. Next what we have twist is 0 and twist location 0.25. Twist is 0, twist location is 0.25, and dihedral angle is 5. So dihedral angle is 5. I'll change this 0 to 5 as per my design requirement and I will enter. Okay. Next what other parameter we have? Next the aerofoil. Okay. So which aerofoil we have to add? NACA 2212. Okay. So everything is done here except the aerofoil. So now default aerofoil we have NACA 0010. So this aerofoil we have to change. Okay. The name of this aerofoil is NACA 0012. We don't want this aerofoil. Aerofoil we want? We want to place this aerofoil. Okay, for our aerofoil cross section, that is NACA 2212. So that's why thickness to chord ratio have to maintain 12%. Thickness to chord ratio here is 10%. I'll change this 10 into 12%. Okay, and next camber is 2% and location of camber is 20% from the leading edge. 2% is 0.02, enter. Location of camber is 20% from the leading edge. So see, the aerofoil name has been changed from 0010 to 2212. This is our required aerofoil 2212. So 2212. So everything is done now. Yes. So all parameters are done, which means you have generated your required wing. Right? I'll share this. See. So we have done with our wing, right? As per our requirement. Same, right? Yes. I'll just show wireframe mode because currently I've shaded now. Change the shaded into wireframe. Come to yes, surface. Okay, yeah. it's completely same, right? So this is how you can design your required wing. Okay, in this OpenVSP we have the wing. Okay, that is default wing. By using this default wing, okay, you can create or you can design your required wing. Okay, as per your requirement, whatever parameter you have or whatever parameter you want to place for your wing design, that parameter you can use and you can create or you can design your required wing, okay, in this OpenVSP software. So this is all about today's topic. Okay, thank you to all. We'll continue in the next class. So we have created a 3D wing by using 2D parameters or wing design parameter. Thank you.
Thank you, sir.
Okay.